Are you offering 541 and next semester too?
541, probably not. So usually the 500 level classes are on a rotation like
Yeah,
three.
it's usually one a year or like.
Yeah. Is 540 being offered? I don't even know. Is 540 listed on there?
No, they don't have.
Oh, okay.
They do have 541 though.
Oh, really? 541 again?
I think it's a bug.
Oh, okay.
It's really weird.
Wait for, what is it, for fall?
For, no, this was.
Well, we're in spring right
For
now.
fall, where you for fall. Yeah, because the next. So check for fall. Yeah. Yeah, they have it. No.
I don't think she's.
Like. Yeah. Yeah, when is it gonna be registered to call classes? I don't know.
Don't let it start, I guess. I'm not involved.
They haven't opened it yet. They do.
All right, it's 5:30. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? And in there, got one more week after today for spring break. I was telling my class before this. Normally, spring break is the 10th week of the spring semester, but I think because of the leap year, it's delayed a week. So we got to go one more week before we get on spring break. So we're almost there. Okay, so plan for today is we're going to continue our discussion of strong and weak forms. Today we're going to focusing mostly on the weak form. So we're going to derive what it looks like. We're going to find out how to find solutions for it. And this will basically set us up to for our next unit, which is finite element forms. Okay. All right. So announcements. So the due date for ANSYS Activity 2 member has been pushed back, and so originally it was due next Friday. But I pushed that back until the following Tuesday. So that's Tuesday, April 2nd. Okay. So just to give you guys a bit more time to work on that. You know, especially the coding portion. So, you know, if you haven't done the coding portion yet, it's definitely something to practice. Because it's honestly that question there is going to be a good warm up for our final project, which is going to be you know, more coding. Okay. All right. I think that's it. Not much more to announce. Are there any questions I can answer before we get started for today? Okay. All right. So the where we're going to start today is with the weak form of a boundary value problem. Okay. So last time we were here on Tuesday, you know, we introduced this idea of a boundary value problem which is nothing more than just a differential equation applied to a certain geometry with boundary conditions, right? So those are the three components of a boundary value problem. And what we did last time was we kind of did a review of differential equations where, if you have a differential equation, maybe something looks like this, right? We could solve for its solution, apply the boundary conditions, and so on and so forth, okay? And then eventually you're going to get your solution, the solution to your problem, which is a function of x in this case, okay? So that's probably the standard way, or I think the way that probably most people learn how to solve differential equations is through this method, either direct integration, or maybe use an integrating factor, or use the characteristic equation, things like that. Okay. So we're introducing this concept of a weak form, which is the same problem, right? So I want to emphasize that a weak form is no different than the strong form. So if you solve it exactly the same way, you get the same solution. It's just that it's presented in a different way, or in a different mathematical form that makes certain things more convenient. Okay. And so we kind of left the lecture on Tuesday with this concept right here, where if we look at this quantity in parentheses here, okay, this quantity that I just circled in red, that is our standard kind of strong form differential equation. That's our strong form. And then what we're doing to the strong form is we're going to be multiplying the entire equation by this function w of x. Okay. Where this w of x, we define it as the weighting function. Okay. So we're taking our original differential equation, we're multiplying by this weighting function. Now this kind of gives us some new tools to play with for manipulating our solution. Okay. And so what we did from here is that we took our weighting function, we took our equation here, and we integrated it over the entire problem domain, right? And so for each of the terms that we're integrating it, since it's just a 1D case, we're working in just a 1D system here, we're integrating it from 0 to L. Okay. So this first term integrated from 0 to L, and the second term we're integrated from 0 to L. Okay. And so the very last thing that I left you with was the fact that, now that we have it in this form right here, now that we have this weighting function, we have this integral here, right? These are kind of two ingredients to kind of allow us to do something really special, which is integration by parts, which is what's going to kind of facilitate our weak form. Okay. So we're going to start there. So where we're going to start today is deriving the weak form deriving the weak form of a boundary value problem. Okay. Okay, so let's start. So let me start with the integral. Okay, so let me go ahead and I'm just going to rewrite the integral that I had up there. Okay, so integral from 0 to L and w of x multiplied by d dx of EA du dx. Dx plus integral from 0 to L of w of x, b of x, dx. All that's equal to 0. Okay. All right. So let's talk about the weighting function first. So before we actually do integration by parts, let's talk a bit about w of x. Okay. So like I said, w of x is our weighting function. Okay. And the weighting function is, you can think of it as a function that is mostly a mathematical tool, right? It's not something that we're going to solve for. Okay. So ultimately, it's not something that we specifically have to worry about. But this wvex function, in order for it to be useful for us, it does have to have certain qualities or certain characteristics. So we're not going to be able to talk about all its characteristics just yet, just because it doesn't really make sense right now. But the most important characteristic that we want to talk about right now is that these weighting functions have to disappear at the locations of the Dirichlet boundaries. Okay. So basically, whenever we have a Dirichlet boundary condition or a boundary condition where we're directly specifying the value of u, then w of x must be 0 at those locations. So for example, right? So kind of the assumption or kind of the geometry that we're kind of working with in this problem kind of looks like this, right? Right. So we have a rod here. It's fixed to the wall at x is equal to L, right? Right. So what that tells us is that u of L is equal to 0, right? That's our Dirichlet boundary condition. Okay. If u of L is equal to 0 there, or if we have a Dirichlet boundary condition, that means w of L must also equal 0 as well. Okay. So if u of L is equal to 0, therefore w of L is also equal to 0. If you've never seen those 3 dots before, they look like if you watch Dragon Ball Z, they look like the pattern on Krillin's head, but that means therefore. And this is even true when our Dirichlet boundary condition is non-zero. So eventually, what we're going to see is we're going to talk about heat transfer, and the heat equation. So even when we have a Dirichlet boundary condition on the temperature, the weighting function has to be 0 there as well. We'll kind of get to that. Okay. But for now, this is the most important characteristic that we have to do. The weighting function is going to have other characteristics that we're going to talk about, as it becomes pertinent. But for now, this is the one that we need to work. Okay. So with that in mind, with that in mind for the weighting function, let's go ahead and apply our integration by parts. Okay. So if you notice, kind of back in our form here, we have 2 integrals, right? So we have the first integral, the one which has all the derivatives, and the second integral, which involves the body force term. So the second integral, we're mostly going to leave this alone for now, right? So we don't really need to do anything here. It's only this first integral that we need to work with because we need to move some derivatives around. Okay. So let me go ahead and copy this integral down here, just so it's a little bit easier to work with. So we have integral from 0 to L, w of x, d dx of e times a du dx dx. Okay. Let's integrate this by parts. And so if you don't remember how integration by parts work, basically we're going to take our integrand, or basically the function that we're taking the integral of, and we're going to break it up into two. Okay. So I'm going to take one portion of the integrand and define that as w of x. Okay. And so I'm going to define this as a function u. Okay. I'm going to use another u sign. Okay. And then we're going to take the other portion of the integrand and define it as another part called dv. Okay. So dv is equal to d dx of ea du dx. Okay. And so the way this works is that, for the whichever part of the integrand that you chose as u, we're going to take the derivative of this. Okay. And so we get a quantity du instead. So we're going to take the derivative of w of x, and so the derivative of w of x is just dw dx. Okay. There's not much more we can do at this point because we don't know exactly what w looks like. Okay. And then for the quantity dv, we're going to do the opposite. And so for dv, what we're going to do is we're going to take the antiderivative. Or in other words, take the integral. Okay, so we're going to take the antiderivative of this. This works out pretty well actually because we have a d dx right here. Okay, so taking the antiderivative is just going to cancel out this term right here. Okay. And so our value for v here is just going to be whatever's inside there. So it's going to be ea du dx. Okay. Now that we have these four terms defined here, to perform our integral, so to perform the integration by parts. Oh, yes, good. Thank you for doing that. So the dx goes here. Yes. Yeah, so the question is, do we need to include the original dx into the equation here? Yes, we do. So the dx has to go there. And then when we take the u du here, there's another dx that shows up right there. Thank you. That's a really important part. Okay, so to perform the integration by parts, okay, we're going to compute the following quantity. So we're going to take u multiplied by v. Okay, so we're going to take this and multiply this down here. Okay, minus the integral of v du. Okay, so this just like this. Okay, so let's compute that. So we have u times v. So u times v is w of x times ea du dx. Okay. So that term there is integrated already. So we don't need to do anything more. So we can evaluate this at our bound. So this is evaluated from 0 to L. Okay. Minus integral of dw dx times ea du dx dx. Right. So we did our integration by parts and we ended up with another integral. And so it kind of seems like we didn't really do anything, but we kind of rearranged our equation here to be in a little bit of a nicer form. Okay. Okay. So before we do that, though, let's evaluate this term, because now that this term is completely resolved, we can evaluate this term at the bounds of the integration. Okay. And so we're going to take that quantity, we're going to evaluate it at x is equal to L first. So we have W of L times EA du dx at x is equal to L, okay, minus W of 0 times EA times du dx at x is equal to 0. Okay. Okay. And then we have minus integral from 0 to L dw dx times EA du dx dx. Okay. At this point, let's remind ourselves what our geometry looks like here, right? And so our geometry here looks like the following, right? We have a rod like this, it's attached to a wall. Okay. We're fixed at x is equal to L. Okay. And then on the left side, we have our load, we have our Neumann boundary condition. Okay. So at x is equal to 0, we have our Neumann boundary condition, which is E times du dx is equal to minus the tension. Okay. So coming back to our weak form here, what do we notice about the first two terms, right? This first term is a term that's evaluated completely at x is equal to L. And then this term, the second one, is evaluated at x is equal to 0. Okay. In other words, both of these terms here are only evaluated at the boundaries of our domain. Which means that these are kind of a natural place, or kind of the boundary conditions kind of naturally came out from this formulation. So that's great, right? And so that was one of our goals that we were trying to achieve back from the beginning, where it would be great to have a formulation which baked the boundary conditions directly into the formulations. This is really good here. Okay. Okay. So let's go ahead and evaluate these, because we can actually simplify this a bit, right? Let's start with the first term. Okay. So this first term is evaluated at the Dirichlet boundary condition, right? So our Dirichlet boundary conditions at x is equal to L. Okay. What did we say was a requirement for our weighting function? Right? We require that our weighting function is going to disappear at the Dirichlet boundary conditions, right? So we should have W of L is equal to 0. Or at least that's one thing that we're requiring. Okay. So what that means is that this entire expression here is going to cancel out. Okay. Let me use a different color. There's a little too much red going on there. So this is going to cancel out. since W of L is equal to 0 at Dirichlet boundary. Okay. So that's good. So that simplifies it, and it takes care of the Dirichlet boundary condition at the same time. Okay, so that's great. Okay, so let's look at this other term. So this other term, it's evaluated at x is equal to 0. And what do we have at x is equal to 0? We have this, right? We have the product of E times du dx must equal to minus t. Okay. And look what we have here. We have E, we have du dx. Okay. And so we can substitute that for t. All right, and so that's great. And so now we can kind of put all this together. So after okay. So the weak form of this particular problem is the following. So we have our Neumann boundary conditions. We have W of 0 multiplied by T bar multiplied by A of 0, okay, minus integral from 0 to L dw dx multiplied by EA times du dx okay, plus we still have our body force term, so integral from 0 to L of W of x, B of x, dx equal to 0, okay? Where W of L is equal to 0, okay? So that right there is the weak form of our boundary value problem. Okay? Looks like a mess. It looks like I deceived you, right? So I kind of told you that we're going down this path to make things easier for us to solve. This does not look easier for us to solve. This looks like a gigantic mess. But trust me that this is actually this is actually going to be really helpful for us. All right, any questions on this so far? Okay. All right, let's analyze this a bit and let's talk about some of the important characteristics of this. In particular, I want to focus on this term, but this is kind of where most of the magic happens right here. Okay. Okay. So this term. So the first thing that should stand out to you about this term is that the highest order derivative that we have is 1. So that's really nice, right? So going down from basically a second order differential equation to a first order differential equation. Granted, we have 2 functions to worry about now, but you know that's a very important characteristic for us that we're going to exploit, you know, later on. The other thing that you should notice about this is that it is symmetric. Okay? So we have a first order derivative on W and a first order derivative on U. Okay. It's a little bit hard to see at this point, just because you know there's quite a few steps that we need to do to get there. But what this is going to do is that this is going to create for us a symmetric element stiffness matrix. All right, so one more piece of trivia before we move forward. So what we just did here was kind of what I consider to be the mathematical derivation of a weak form. But this exact form here, you can obtain it in a different way. You can obtain it from a more physical way. And in fact, this exact derivation actually kind of plays out like this in an advanced solid mechanics course. But in that kind of course, this is typically called the principle of virtual work. So it's a real thing. This is not something that I just made up just because I love integrals and derivatives. Okay. All right. So next thing that we're going to do. So now that we've kind of been introduced to this concept of a strong form and weak form. We're not quite ready to solve for solutions just yet. That'll be kind of the last thing that we do today. But let's kind of apply this thing to heat transfer. So let's look and see what the strong form of the boundary value problem would look like for a 1D heat conduction problem. Okay. So this is mostly just for terminology. And so, we're, for the most part, for the next few weeks, we're going to be working kind of purely from the mathematical equation. So whether we call it K, we call it E, or if we solve for U, we solve for T, it's marginally inconsequential, but, because their equations look exactly the same. It's just that it's kind of important to kind of establish term. Okay. All right. So the heat conduction problem, the geometry here looks very similar, right? Because we're in 1D, right? There's only so many one-dimensional shapes that you can draw. Okay. All right. So we have our rod here, but now if you want to talk thermal engineering, this is like a fin. Okay. So we have our fin here. Okay. And what we have instead of a fixed displacement, instead of having zero displacement, we have a fixed temperature. Okay. And so our Dirichlet boundary conditions are now T, in this case, it's T of 0 is equal to T naught. Okay. So I think that's an important distinction. So now our Dirichlet boundary conditions are non-zero usually. Okay. Unless you're simulating heat transfer in a block of ice, which is possible, I guess, as well. Our Neumann boundary conditions are now, instead of a stress, we are now calling them a heat flux. Okay. And so what we have here is the symbol we call for it is Q bar. Okay. And the formula for this is K times dt dx is equal to minus Q bar. Okay. Let's define the material properties for this fin. So the material properties, we have K. So K is called the thermal conductivity. Okay. The thermal conductivity is a parameter that is used in heat transfer to describe how well heat can transfer through a material. Okay. Generally, metals will have a much higher thermal conductivity than non-metals. Okay. Metals conduct heat a lot more quickly. Okay. You'll learn that by example if you ever go to a Korean restaurant that serves you hot tofu soup in those tin cans. or there's tin bowls and you try to grab it with your hands and you regret it afterwards. So yeah. Porcelain bowls are the way to go, not metal bowls. I don't know what Koreans are thinking. Okay. And the other parameter that we have here is A, where A here is the same interpretation as before. So A is the cross-sectional area. All right. So the other thing that we'll define here, very similar to the body force, is that we may have some internal heating. Okay. So maybe our material is laced with so maybe like an electric heater on the inside, or maybe it's by some like reactive material that's producing heat. Okay. And so we may have a function S of X. And so S of X is what we call the thermal generation function. Yes, so we haven't introduced A into the equation yet, but the A will show up when we write out the differential equation. Yep. Okay. And so in these problems, what we're interested in solving for is we're interested in solving for the spatial distribution of temperature within the geometry. In other words, T, we're solving for some function T of X. Okay. All right, and then our differential equation, or the main governing equation that we're going to do to solve this in the strong form is we have d dx of k times a times dt dx plus our thermal generation function S of X is equal to 0. So mathematically, if you compare this to our 1D elasticity equation, this is mathematically identical. The only difference is that instead of solving for U, we're solving for T. Instead of the Young's modulus, we have a thermal conductivity K. The area, oddly enough, makes an appearance in both equations. And instead of a body force term, we have a thermal generation term. Okay. So the names of the terms change, and the symbols that we use for the terms change, but mathematically this is identical to 1D elasticity. Okay. All right. So I'm skipping the derivation of this equation, but just know that you can obtain this equation by applying conservation of energy inside the material. Okay. All right. Any questions on this so far? Okay. All right. A bit more terminology before we move forward is that I'm going to generalize the definition of the boundaries. Okay. So this is going to be important for us as we define our weak form and kind of the general form. Okay. Because what we did so far, so what we did with elasticity was we derived the weak form for a specific case where the Dirichlet boundary condition was that x is equal to L and the Neumann boundary condition was that x is equal to 0. Okay. You can see from my geometry here, I drew it kind of opposite with T of 0, x is equal to 0 is our Dirichlet boundary condition, and our Neumann boundary condition is at the other side. But it would be good to have kind of, terminology and terms for kind of the general case where we can kind of swap these terms interchangeably. Okay. So generally speaking, when you're talking about kind of mathematical descriptions of domains, right? When you have this kind of gamma symbol here, right? Gamma symbol refers to the domain of a particular, or excuse me, the boundary of a particular domain. Okay. We can add subscripts here to denote kind of which boundaries are Dirichlet boundary conditions and which boundaries are Neumann boundary conditions. Okay. So if we do like a gamma subscript U, right? This refers to the locations of the Dirichlet boundary conditions. Okay. So in other words, what we can say is that T of gamma U is equal to T naught. Okay. And so if we compare that to the previous kind of more specific case, in our specific case up there, gamma U is equal to refers to X is equal to 0. Okay. Okay. So wherever you have your Dirichlet boundary condition, that's where gamma U refers to. Okay. And then gamma H, or excuse me, gamma T, this refers to the location of the Neumann boundaries. And so for you to write kind of the generalized form of our Neumann boundary condition, we have K times dt dx at X is equal to gamma T is equal to minus Q bar. Okay. Okay, so that's going to be important because when we define our weak form for the heat conduction problem, and you can apply this for our 1D elasticity as well, we want to use these kind of general terms for the boundary so that our formulation can be flexible to whatever our geometry looks like. Okay. So now with these terminologies and kind of with all the symbols and terms and parameters introduced for heat conduction, we can now present the weak form of the 1D heat conduction problem. Okay. And so, of course, to obtain this weak form, we'd follow the exact same process that we did earlier in the class today. And so you would take your strong form equations, you'd multiply by weighting function, you integrate it from 0 to L. Okay. And then you do your integration by parts, and then you end up with the following result. Okay. So relative to that expression that I had up there, some of these terms here are moved around a little bit. This is a little bit more, I would say, classical in terms of where the terms were located, but all the terms are still present. They're just moved around on sides of the sign, mostly just to make things positive. All right, so we have integral from 0 to L of dw dx times k times t, or k times a, excuse me. K times a times dt dx okay, is equal to integral from 0 to L of w of x s of x dx plus our Neumann boundary condition term. So we have quantity w times k times a dt dx, all evaluated at x is equal to gamma t. Okay. where we also have the following properties. Where if we evaluate the weighting function at the location of the Dirichlet boundary, so we say W evaluated at gamma U, okay, is equal to 0. And then T evaluated at gamma U is equal to the Dirichlet boundary condition, so T naught. Okay. So that's our weak form. So, looks very similar to our weak form for 1D elasticity. The biggest difference here is that I use kind of our general boundary terminology instead. So instead of x equal to 0, x equal to L, I use the terms, gamma T and gamma U. Okay. All right. Any questions on any of this so far?
Gonna have always the S of X for all of them.
Yes. Yeah, S of X is always going to be given to you. That's one of the inputs to the problem. A lot of times it's going to be 0 because a lot of times, thermal conductivity is pretty rare. But it'll always be given to you. Okay, so let's do a couple of examples. And the main reason I'm bringing up heat conduction, as you'll see, is that as we kind of move on from this point in the class, we're going to do more heat conduction type problems. In 1D, it doesn't really matter because 1D, displacement and temperature, they're both scalars. But eventually we're going to be doing 2D formulation, so 2D finite elements. Heat transfer is a lot easier to solve in 2D just because temperature is a scalar quantity. Whereas if you go into 2D for elasticity, your displacement or your deformation now becomes a vector. And that becomes infinitely more difficult to deal with. And so you're going to see a lot more kind of heat conduction type problems, heat transfer type problems as we go in the class. Okay. Okay. So let's do another example. We're going to do a strong form solution, and then we're going to do an approximate weak form solution. Okay. All right. So this is the situation, or this is the problem. So we have our rod here. We'll say that at x is equal to 0, we have our fixed temperature here. So we have T naught. Our applied temperature is 25 degrees Celsius. Okay. And then on the other end of the rod here, we have a Neumann boundary condition, but it's going to be fully insulated. A fully insulated part here basically means the derivative of the temperature, dt dx, is going to be 0. Okay. All right. The other thing that we'll have in this problem, it is unusual, but it's going to be important for highlighting something in the solution, is we actually are going to have some thermal generation here. Okay. So our thermal generation S of x here is going to be x squared over 5. Okay.
Explain what thermal generation is.
Yeah. So thermal generation, it represents like, if you were taking a material by itself, it's the ability for the material to generate heat on its own. So most oftentimes this occurs where you have kind of a very thin kind of electric heater. Sometimes you have that kind of sandwich in between two different types of materials. And so that heater, will be generating heat just through electricity. And so when you're solving for the temperature in that entire solid, that thermal generation needs to be taken into account. The other common case is that maybe you have a material that has some chemical reactions kind of going on the inside. So the most common case would be like kind of like a heat pack or like a cold pack. Just one of those things where you kind of like snap it and then it kind of generates heat, stuff like that. So it's a material where there's some kind of reaction or some kind of additional energy that's coming in that's generating heat. Yeah. All right. And then we have our properties here. So we have our thermal conductivity. So thermal conductivity here is 2. these units always trip me out. So we have joules per meter degree C seconds. Okay. It's just 2, but I have the units there to be consistent. And then our cross-sectional area here is 0.5 meter squared. Okay. The important thing is that these properties are constant. Okay. So they don't depend on this. Okay. Oh, the length. And so we also need the length. And so this we'll say that the length of this fin is equal to 5 meters. Okay. All right, so with all this given information, what we're going to do is we're going to solve the strong form first. For the distribution of temperature in this rod. So we're going to solve our differential equation and get its solution. Okay. All right. So let's start with our strong form equation. So our strong form equation is d dx of k times a dt dx plus s of x is equal to 0. Okay. Let's go ahead and plug in for all the parameters here. So let's plug in for the thermal conductivity. We'll plug in for the cross-sectional area, and we'll plug in for the thermal generation as well, S of x. Okay. So when we plug in K and A, we're going to take 2 multiplied by 1/2. And so 2 multiplied by 1/2 is just 1, right? And so this first term here becomes d squared t dx squared. Okay. Plus S of x here given to us was x squared over 5. And all that's going to be equal to 0. Okay. So we have another pretty straightforward case here. So there's not much for us to do. So let's subtract x squared over 5 from both sides. So we have d squared t over dx squared is equal to minus x squared divided by 5. Okay. Let's integrate both sides. Okay. So this is an equation we can solve just from direct integration. Okay. So we integrate both sides. On the left-hand side, we have dt dx is equal to. We take integral of minus x squared over 5. That's going to be minus x cubed over 15. Okay. Remember, we need to add our C1 there. Let's integrate this one more time. So we integrate it one more time, we get e of x is equal to minus x to the 4th over 60 plus C1x plus C2. All right, so that right there is our general solution. Okay, so let's apply boundary conditions to this now. Okay. So we have 2 boundary conditions in this case. So we have the boundary condition at x is equal to 0. Okay. So at x is equal to 0, we have our Dirichlet boundary condition. So that the temperature at x is equal to 0 is equal to 25 degrees C. Okay. And then at x is equal to L, we have our Neumann boundary condition which states that dt dx at x equal to L is equal to 0. All right. So let's use these two equations to solve for our constant C1 and C2. Okay. All right, so let's start with the first boundary condition here. So we'll take our solution and plug in x is equal to 0. And so if we do that for our general solution, we have minus 0 raised to the 4th power divided by 60 plus C1 times 0 plus C2. Okay. And then by the boundary condition, this must equal 25. Okay. And so that tells us that C2 is equal to 25. Okay. And then for the second boundary condition, we have dt dx. We know from our general solution procedure, dt dx is equal to minus x cubed divided by 15 plus C1. Okay. If we apply this at x is equal to L, okay, we get minus L cubed over 15 plus C1. That's equal to 0. Okay. We know that L is equal to 5. And so let's go ahead and plug that in. Okay. So we get C1 is equal to 5 cubed divided by 15. Okay. We could factor out a 5 from the denominator because 15 is just equal to 3 times 5. And so we cancel out that 5 on the denominator with the 5 on the numerator. We get 5 squared over 3, which is 25 over 3. Okay. All right. So we plug both those in and we get e of x equal to minus x to the 4th divided by 60 plus 25 over 3x plus 25. All right. Any questions on that example there? How we got everything? Okay. All right. So that looks good, right? So between this example and the one we did on Tuesday, you know, we've had plenty of practice solving strong form equations. Right? But what about the weak form, right? So we've spent all this trouble, we've derived the weak form, but we haven't really done anything with it. We just kind of stated that it's there. Okay. So one thing that the weak form allows you to do, or one thing that's a lot easier to do in the weak form than is in the strong form, is to find what's called approximate solutions. So we have approximate solutions to our weak forms. Okay. So what we've just done with the strong form is we found what's called an exact solution, right? So we solved our equation in the exact way. Okay. There might be situations where we don't want to look for an exact solution, or I guess to be more accurate, there will be some situations where we can't find an exact solution. And so in those cases, you know, it's actually going to be easier to find an approximate solution. So a solution that we know may not exactly solve the equation, but it's going to be pretty good. And, for the next 20 minutes, you're probably going to look at me and think that I'm crazy, right? Because, we in these 1D equations, we have situations where we can find the exact solution. So why would we ever want to, find something that's inferior? Well, when we get to multiple dimensions, when we get to 2D and eventually, 3D, we're not going to do 3D in this class, but you can imagine that it gets there. It becomes a lot more difficult to solve these partial differential equations. And so in those cases, finding an approximate solution is actually really helpful, because then that actually lets you solve something. It may not be exact, but in a lot of cases, it's going to be pretty good. And if you refine your mesh enough and you do some certain things, it's going to give you a really good solution. Okay, so how do these work? So how do we find an approximate solution? An approximate solution, it kind of takes our solution procedure and kind of flips it on its head. Okay. And so what do I mean by that? And so, when we solved our exact solution, when we kind of started this process of getting this result here, we had no idea what the solution would look like, right? We had no idea what kind of functional form it would take. We have no idea what kind of polynomial it would be, if it would even be a polynomial at all, right? We just solved the equation. We just ended up with this, okay? For an approximate solution, we kind of go backwards. And so for an approximate solution, the first thing that we do is we have to assume the functional form of the solution. And so in a lot of ways, it's kind of backwards compared to what we do. So, instead of letting the solution kind of speak for itself, we're making the assumption right from the beginning that the solution is going to look like the problem. Okay. So, from the last problem, you can see here that our solution ended up being a fourth order polynomial, right? So we have an x to the fourth term. Okay. What if we did it backwards? So what if we said that, we have this equation here, we have this problem, but instead what we're going to say is that, all right, we're going to find a quadratic solution. Okay? And so what we say is that our t of x is going to be some quadratic function. Okay? We don't know exactly what the quadratic function is going to look like, but we know that the highest order polynomial there is going to be 2. Okay. And so what we can say instead is that our t of x is equal to a0 plus a1 times x plus a2 times x squared. Okay. So that's the most general form, or the general, most general expression for a polynomial of order 2. Okay. And so now, now what we have here is 3 unknowns. So our knowns are a0, a1, and a2. Okay. And so to complete our solution, we have to find out what's the most optimal value of these coefficients that will make our solution as accurate or as faithful to the governing equations as possible. Okay. So now instead of solving for a whole function, what we're solving for instead are just the values of these coefficients. Okay. Which, when you kind of extrapolate this to higher dimensions in 2D and 3D, is a much simpler problem than trying to find a whole function just from scratch. Okay. Okay. Not only do we have to do this for the solution, But remember, we're doing this for our weak forms, right? And so our weak forms have that weighting function that's there as well. So another requirement for the weighting function. So this is kind of, a follow-up to kind of what I was kind of teasing at the beginning of lecture. Okay? So our weighting function in the weak form must have the same functional representation, or must have the same functional form as our solution. Okay? So if we're going to assume that our solution is a quadratic function, then our weighting function must also be a quadratic function. Okay? So we have w of x equal to b naught plus b1x plus b2x squared. Okay. Granted, its coefficients are going to be different, so that's why we're using b's instead of a's, but it has the same three terms: constant term, a linear term, and a quadratic term. Okay. All right. And so now the game that we're going to play here is we're going to try to solve for those coefficients. All right. So that's the idea. So to find an approximate solution, you have to first assume a functional form. And then you're going to find basically the best version of that function that satisfies your equation. All right, any questions on this so far? Okay, all right, so let's do an example, or let's redo the previous example. Let's find an approximate solution. Okay. So just to kind of remind you, our in our last example, we have k is equal to 0 or 2. A is equal to 0.5. S of x is equal to x squared over 5. Okay. Our Dirichlet boundary conditions, we have t of 0 is equal to 25. And our Neumann boundary condition as dt dx at x is equal to L is equal to 0. Okay. Okay. So first thing we're going to do, before we even bring up the weak form, is we need to make sure our approximate solutions exactly satisfy the Dirichlet boundary conditions. Okay. The first thing we're going to do is we're going to apply our Dirichlet boundary condition to t of x and w of x. Okay. So our boundary condition is t of x is equal to 0 is equal to 25. Okay. If we plug that into our our general equation here, so what we're assuming is that our t of x here is going to be a0 plus a1 times x plus a2 times x squared, right? That's what we're assuming. We're assuming a quadratic solution. Okay. If we evaluate this at x is equal to 0, then we know that every term here with x is going to be 0. Right? So this is going to be 0. This is going to be 0. Okay. All right, so then what that tells us is that we're able to solve for one of the coefficients right away. So one of the coefficients we find is that a0 is equal to 25. All right, question. So how do we choose a form to use in these approximations? Yeah, that's a great question. Um, so when we do finite elements, there's a limited amount of functions that you can use in finite elements. Basically, it's just going to be a linear function or quadratic function. But when you're finding just approximate solutions on their own, it's really kind of up to you, kind of what functional form that you want to choose. Generally speaking, the higher order polynomial that you use, it's going to yield a more accurate solution. And so if we use a cubic function, that's going to be a more accurate solution. Granted, it's going to be more expensive or more costly to do, but you can do that. But to kind of answer your question of kind of where we're going with this, is that mostly we're going to be limited to just linear functions and quadratic functions. Okay, now let's do the same thing for w of x. Okay, so we're going to apply x is equal to 0 at w of x. Remember, our weighting function here has a different requirement for the Dirichlet boundary condition, that our weighting function has to disappear at the Dirichlet boundary condition. And so instead of equaling 25, when we apply x is equal to 0 to our weighting function, that whole thing must equal to 0. Okay, so then we plug x equals 0 here. We have b0 plus b1 times 0 plus b2 times 0 squared. Okay. Once again, we have all the terms that are multiplied by 0 are going to cancel out. Okay. And then what we get from this is b0 is equal to 0. Okay. All right. So that's always the first step. So whenever you're doing a weak form solution, first step is to apply the Dirichlet boundary conditions and use that to solve for the coefficients. Okay. Any questions on this so far? Okay. All right, so we have 5 more minutes. We're not going to be able to finish this example in 5 minutes. I hate to leave an example kind of like at this stage right here, but I also don't want to hold you guys. So let me start the next step just so you can kind of see where we're going, and then we'll finish this up on Tuesday. Okay. Okay, so the next step here is now that we've solved these coefficients, is we're going to plug our approximate forms into the weak form. Okay. So our weak form for 1D heat conduction is integral from 0 to L dw dx times k times a dt dx dx. Okay. This is equal to integral from 0 to L wx s of x dx plus w times k times a dt dx evaluated at the Neumann boundary condition. Okay. So before, when we had this weak form like this, we couldn't really proceed any further because we didn't know what w of x or t of x looks like, right? But now that's kind of a remedy, because now we know, or at least we know what w of x and t of x want to look like. We know that we want these to be quadratic functions, right? And so into this, we're going to plug in d dx of what we have remaining of w of x. So w of x, all we have remaining is b1x plus b2x squared. Okay. For dt dx here, we're going to plug in d dx of our t of x function, which is 25 plus a1x plus a2x squared. Okay. Same thing for w of x here. We're going to plug in b1x plus b2x squared. Okay. And we can actually evaluate this term as well. This is actually going to simplify quite a bit for us because we know that the Neumann boundary condition here is x is equal to L. Okay. And it just so happens that x is equal to L, we know that we have a fully insulated boundary condition. So the derivative of the temperature dt dx is equal to 0. Okay. So that means this whole term here, for this problem, not true in general. So for this problem, this is going to go away. Okay. So that saves us a little bit of writing from there. Okay. And we also know L is equal to 5, so we can plug into that as well. Okay. So let's go ahead and plug all these in and then we'll call it a day. Okay, so we plug all these in, we get integral from 0 to 5 dw dx, and so we take the derivative of w of x, we get b1 plus 2b2x. Okay. The product of k times a, k is 2, a is 0 is 1/2, so that cancels out to 1. We have the derivative of dt dx, which is a1 plus 2a2x dx is equal to integral from 0 to 5 w of x here, which is b1x plus b2x squared times s of x, which is x squared over 5 dx.
Would be a 25, the W.
No, because b0 is 0 because the traditional boundary condition disappears. The Ka canceled out. So in this case, K for this particular problem, K is equal to 2 and A is equal to 1/2, 0.5. So 2 times 1/2 is just 1. So I chose the numbers for this problem to be convenient. All right, and so when we come back on Tuesday, we'll go ahead and evaluate this. So we have some more integrals to do. But eventually what we're going to be able to find is that this is going to give us a linear system of 2 linear equations or 2 unknowns that we can solve for A1 and A2. Okay. All right, so thank you guys for coming today. Hope you guys enjoy the rest of your day. Hope you guys enjoy your weekend. Oh, by the way, so next week I'm planning on being sick. So I'm planning on getting sick all weekend and I won't be able to come to work. It's awful. So next week, all the lectures will be virtual. So I'll be working from home. So you'll probably get an email from me on Monday saying, oh, I'm really sick. I can't come to work, but I'm just warning you guys ahead. Okay. All right. So thank you guys for coming today. Hope you guys enjoy the rest of your weekend and I will see you guys next week. Sure. What's up?
What?
No, that's
Oh, yeah. Oh.
Oh, sorry, Brianna. Are you hang on, let me turn on the volume. Oh. Yeah, the weighting function. It is a bit confusing right now. And honestly, we haven't reached a point where we can kind of fully appreciate it. But so just for now, you can just kind of consider it to be like just a tool, just like something like a mathematical tool that we're just using to make things convenient. It honestly, we won't really get to really fully see it until we get to the finite element part, which is going to be next week. Yeah. But for now, it's just kind of just you gotta trust me. It's important, and it'll become clear next week. Yep.